Hello, my name is Liam Gleason, and this is Lab 1 Constant Velocity for Physics 1-2211 at Georgia Tech. Now, the purpose of this lab was to compare the actual observed motion of an object, a real object, moving at constant speed, and compare that to a computational model mimicking the movement of the object at same velocity and same constant speed. Now, we used the tracker we use the website tracker to track the position of the object at many different time steps, as you can see here. The marker, or the object we used, was a marker, and that is the system, while the surroundings is everything else, such as the table and the air. On the right of the screen, you can see the time step and the X and Y positions, and that was tracked from 0 seconds to 1.4 seconds. And on the left, you can see that the x-axis is placed in the cap of the marker, same with the y-axis, and the position was calibrated using a meter stick in the background so the measurements would be accurate. And as you can see, when I click play, the measurements were tracked over the period as it moved, and it gave us position data we could use for analysis. Secondly, we used Python to create a computational model in GlowScript, and as you can see here, the mass was the same as it was in the video. The initial position is the same initial position as it was in the video. The velocity was calculated using the change in position over change in time from the second measurement and the first measurement. So the velocity is the same as it is in the video. The time step is the same as it was in tracker or in the video, 0.033 seconds. And that goes until 1.467 seconds. Obviously, FNet is going to be 0 because it's constant velocity. We used the velocity update formula, which is VF equals VI plus FNet over M times delta T, followed by the position update formula, which is RF equals RI plus V calculated above times delta T. And we use that to calculate the marker's motion. And as you can see, if I run the program, the movement is simulated and the data is printed out on the bottom here. Now, after we had data from the computational and the actual, we just compared the two. As you can see, the computational is more linear than the actual, and this can be contributed to many things. So the two main ones would be the friction force and force of air resistance acting on the marker in real life obviously caused the actual marker to have a smaller final position than the marker in the computation. And finally, to answer a couple questions for analysis, if I were to change the axis in tracker, if I were to change the positive x-axis to the negative x-axis, then the marker would just be moving in the negative direction. The velocity would be the same, but the position would be in the negative x. And is it possible to calculate how many pushes and pulls are in the object? Yes, there is a positive force going to the right, and that's velocity, and there's a negative force going to the left, and that's friction, and those are canceled out. And the force of gravity going down and the normal force going up from the table are also canceled out, so the net forces on the object are 0, and the velocity stays constant. And that's all for Lab 1. Thank you.